March 17th, 1943, 02:30 hours, bridge of the heavy cruiser Myoko, Bismarck Sea. Captain Seiichi Kinashi stood in darkness so complete that his own hands were invisible before his face. His lookouts, trained through thousands of hours in darkened rooms, their night vision perfected through vitamin regimens and relentless practice, strained into the blackness. They could detect nothing. Yet shells were already falling around his ship with mechanical precision, fired by enemies his crew could neither see nor locate. The Americans had found Myoko from beyond the horizon, their guns directed by technology that seemed to violate the fundamental laws of naval warfare. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. What troubled Captain Kinashi most profoundly was not simply that his ship was under attack from an invisible enemy. In the long history of naval warfare, invisibility had always been relative, always dependent on weather, moonlight, and the sharpness of a lookout's eyes. But now it meant something different, something unnatural, almost inhuman. The Imperial Japanese Navy had known foreign radar before. They had encountered British sets during the Malayan campaign, captured examples from Singapore, and even recovered damaged components from HMS Prince of Wales after her sinking in December 1941. Japanese technical officers had dismantled those units, charted their circuitry, and concluded, with reasonable confidence, that such devices, while interesting, did not fundamentally alter naval doctrine. Those systems were early war instruments built around meter-wave technology, dependent on simple oscillators, mechanically driven antennas, and display systems that demanded extensive interpretation. Their beams were broad, their range resolution poor, and their reliability inconsistent. A clever destroyer captain could confuse or outrun them. Smoke, rain, or chaff could disrupt their returns. The Imperial Navy's greatest strength, its night-fighting doctrine, remained intact against such primitive tools. Officers like Kinashi were therefore conditioned to view radar as a nuisance, a foreign gadget that might offer early warning but did not threaten Japan's mastery of darkness. They carried this confidence into the early Pacific engagements, where Allied radar sometimes failed outright, sometimes misidentified targets, and often did little more than inform a captain that something was out there. In the Solomons, British-designed sets used by Commonwealth forces rarely provided decisive advantage. Japanese night attack units continued to deliver devastating blows even in waters where the enemy possessed radar. These experiences reinforced the comforting belief that foreign electronics could not and would not overturn the Imperial Navy's carefully cultivated superiority. Yet the Australian systems encountered later at Rabaul, though newer and somewhat more stable, still confirmed that radar as practiced by the Commonwealth was a limited technology. Their coastal warning sets could track incoming aircraft with modest accuracy, but were of little value for naval gunnery or surface combat. They were land-based tools, static, predictable, and wholly unsuited to the complexity of maneuvering ships. Japanese officers viewed them with polite interest, nothing more. They saw no reason to revise their conviction that no radar yet deployed could challenge the knife-edge precision of their night torpedo doctrines. But American radar, true American centimetric radar, was an entirely different creature. Captain Kinashi had heard rumors from other submarine commanders about its uncanny accuracy, its resilience under combat conditions, its ability to detect ships at ranges previously considered impossible. But rumors were one thing, experience was another. What he confronted now was not a foreign version of known technology, but a weapon born of an industrial and scientific culture fundamentally unlike Japan's, a machine that had transformed naval combat so rapidly and so completely that 2 decades of Japanese training had become obsolete in less than 18 months. The American SG radar was compact, rugged, devastatingly precise. Unlike the British and Australian sets, this radar operated in the centimetric band, enabling narrow beams, tight range discrimination, and astonishing fidelity. Even in heavy seas, its rotating antenna swept the ocean with invisible precision, painting the location of every vessel, large or small, with a clarity no human lookout could match. Where British radar offered vague direction, the SG gave exact bearings. Where Australian systems warned of approaching aircraft, the SG tracked surface targets with lethal accuracy. Where Japanese night optics required moonlight, skill, and luck, the SG saw in total darkness as easily as in daylight. But what unsettled Kinashi most deeply was not the SG itself, but the ecosystem of systems built around it. American radar was not simply a device, it was the heart of an integrated combat architecture. Radar information fed into plotting boards, fire control computers, communication circuits, and command centers. Every ship equipped with SG radar possessed a unified picture of the battle, shared instantly across the formation. No Japanese vessel had anything comparable. Not in concept, not in practice, not in potential. The implications were staggering. Japanese destroyers could no longer rely on stealthy approaches. They would be tracked from miles away. Submarines, like Kinashi's, could no longer assume darkness guaranteed safety. Radar would pierce the night with mechanical indifference. Even evasive maneuvers lost meaning when an American destroyer could follow every turn of a Japanese vessel's wake on a softly glowing screen. And it was not just detection. American radar was intimately married to radar-directed fire control. Guns could fire accurately at targets never seen through optics. Shells landed with cold, mathematical precision on ships the gunners could not see, guided not by instinct, but by electronic certainty. This was not warfare as humans had practiced it for centuries. It was something new, something disconcertingly precise, relentlessly mechanical, and utterly unforgiving. Kinashi felt, perhaps for the first time, the sensation that countless Japanese commanders were beginning to experience, the realization that the battlefield was no longer governed by the skill of the individual captain, but by the industrial capacity of nations. Traditional Japanese advantages, training, discipline, courage, intuition, were useless against a foe who needed none of those traits to fight flawlessly in the dark. Machines had replaced men. Electronics had replaced seamanship. The night, once the Imperial Navy's domain, now belonged to the Americans. And as depth charges detonated around his submarine, each explosion perfectly timed, perfectly placed, the product of radar certainty rather than guesswork. Captain Kinashi understood why British and Australian radar had never inspired fear. They were not the future. American radar was. The distinction was not academic. It represented the difference between technological curiosity and existential threat, between an innovation Japanese officers could dismiss and a revolution that destroyed the very foundation of their naval strategy. Understanding why Japanese commanders feared American radar while dismissing British and Australian technology reveals not just technical specifications, but fundamental differences in industrial capability, tactical integration, and strategic vision that decided the Pacific War. The British had actually pioneered radar development. Robert Watson Watt demonstrated the first practical radar system in February 1935, years before American or Japanese development began. By 1939, Britain had constructed the Chain-Home Network, the world's first operational early warning radar system. This network of coastal stations operating at frequencies between 20 to 30 megahertz provided crucial early warning during the Battle of Britain, detecting incoming German aircraft at ranges exceeding 100 miles. The British achievement was remarkable, revolutionary even, but it was fundamentally a defensive system designed for a specific purpose. Chain-home stations were massive installations requiring towers over 300 feet tall, consuming enormous amounts of electrical power, and completely immobile. The radar sets aboard British warships in 1941 reflected similar limitations. The Type 279 surface warning radar could detect large ships at perhaps 8 to 10 miles under optimal conditions, but its accuracy was insufficient for blind firing. The display was a primitive A-scope, showing only range as a spike on a horizontal line, requiring operators to manually rotate the antenna and estimate bearing. Japanese technical officers who examined captured British radar equipment at Singapore in February 1942 found systems that confirmed their assumptions about Western dependence on technology to compensate for inferior seamanship and warrior spirit. The British sets were large, power-hungry, temperamental, and most critically, they provided early warning, but not fire control capability. A Japanese destroyer captain, equipped with superior optical rangefinders and highly trained lookouts, could still dominate a British ship at night because British radar couldn't direct accurate gunfire in darkness. The psychological impact was minimal because the technology didn't fundamentally threaten Japanese tactical doctrine. The Australian radar situation was similar but even less threatening. Australia had received British technology and adapted it for local production and coastal defence. The Australian warning and control system used variations of British chain-home technology operating at similar frequencies with comparable limitations. These systems provided valuable early warning for defending port cities and detecting approaching Japanese aircraft, but they were strictly land-based installations with no naval fire control capability whatsoever. When Japanese forces captured Australian radar stations at Rabaul and other locations in early 1942, they found equipment that was interesting but not alarming. The sets could detect aircraft and large ships at respectable ranges, but they were massive installations requiring substantial infrastructure, electrical power from shore facilities, and teams of operators. More importantly, they couldn't be adapted for offensive naval operations. They were defensive tools, useful for their intended purpose, but fundamentally unable to transform the nature of naval combat. The American development trajectory was completely different from the beginning. The British Teazard mission arrived in the United States in September 1940 with perhaps the single most important piece of cargo transported during the entire war, the cavity magnetron, a device no larger than a hockey puck that could generate microwave frequency radiation at power levels previously impossible. This British invention, delivered to America for mass production, would become the heart of the radar revolution that destroyed Japanese naval supremacy. The cavity magnetron operated at frequencies around 3 gigahertz, using wavelengths of approximately 10 centimeters. This was a quantum leap from the meter wavelength systems the British had deployed. The shorter wavelength provided dramatically better resolution, the ability to distinguish between closely spaced targets, and most crucially, the accuracy needed for blind fire control. The power output of 10 kilowatts from a compact, lightweight device meant this technology could be installed on destroyers and even smaller vessels, not just capital ships or coastal installations. The Massachusetts Institute of Technology Radiation Laboratory was established in November 1940, specifically to develop military applications of microwave radar. Under the direction of Ledoux Bridge, the laboratory grew to nearly 4,000 employees by 1943, a research and development effort that dwarfed anything Japan or Britain could mount. The laboratory's focused mission was not simply to build radar sets, but to revolutionize warfare through electronic detection and fire control. They succeeded beyond anyone's initial expectations. The SG surface search radar emerged from this concentrated effort, operating at 3 gigahertz with 50 kilowatts peak power, weighing only 1,000 pounds, achieving 95% operational availability. This system represented American industrial and scientific capability at its absolute peak. The radar could detect a destroyer at 15 nautical miles with accuracy of plus or minus 40 yards in range and plus or minus 0.5 degrees in bearing. Most revolutionary was the plan position indicator display, a circular screen that showed all contacts in their actual relative positions, updating every 2 seconds, providing commanders with a god's-eye view of the entire battle space. This was not early warning radar. This was not defensive technology. This was an offensive weapon system that fundamentally transformed naval combat from visual engagement to electronic warfare. When integrated with the Mark 37 gun director and analog fire control computers, the SG radar allowed American destroyers to engage targets in complete darkness at ranges exceeding 10,000 yards with first salvo accuracy. This capability had never existed before in naval history. It was exactly what Japanese tactical doctrine was utterly unprepared to counter. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The industrial context separated American radar development from British and Australian efforts in ways Japanese commanders only gradually understood. Britain in 1940 through 1942 was fighting for survival under constant air attack, with its industrial capacity severely strained. British radar development had to focus on immediate defensive needs with limited resources. The systems they produced were revolutionary for their time, but necessarily constrained by Britain's desperate circumstances. Australia's situation was even more resource-limited. With a population of only 7 million people and a small industrial base, Australia could adapt British technology and produce adequate defensive systems, but completely lacked the capacity for breakthrough. Innovations in electronics. Australian radar production focused on coastal defence and early warning systems that served their purpose but represented no advance over British technology. The United States, in 1941 and 1942, faced no immediate threat to its homeland and possessed the world's largest industrial economy. American radar development could focus not on immediate survival, but on offensive systems designed to win the war. The resource commitment was staggering. The Radiation Laboratory alone spent $1.5 billion in 1940s currency, more than the entire gross domestic product of many nations. American factories produced over 100,000 radar sets of all types during the war. Western Electric, Westinghouse, and General Electric mass-produced cavity magnetrons, eventually manufacturing over 250,000 units. Japanese intelligence had observed British and Australian radar capabilities and concluded, not unreasonably, that radar was a defensive technology useful for early warning but not threatening to Japanese offensive doctrine. This assessment was correct for British and Australian systems as they existed in 1941 and 1942. Where Japanese intelligence failed catastrophically was in understanding American industrial capacity and the revolutionary implications of microwave radar integrated with fire control systems. The Battle of Savo Island on August 9, 1942, demonstrated that Japanese assumptions about Western radar were initially correct. Despite having radar-equipped ships, the Allied force was completely surprised by Vice Admiral Gunichi Mikawa's cruiser squadron. Japanese lookouts detected the Allied ships first. Japanese tactics overwhelmed the enemy before radar could provide any meaningful advantage. 4 Allied heavy cruisers were sunk in 33 minutes with minimal Japanese losses. This victory seemed to confirm that radar was no substitute for superior seamanship and night fighting skills. What changed between August and November 1942 was not Japanese tactics, but American technology. The primitive CXAM radar sets present at Savo Island operated at meter wavelengths, with limited range and no fire control capability. They were essentially American versions of British early warning systems, useful for detecting approaching aircraft, but nearly useless for surface combat at night. The SG radar that arrived on American destroyers in late 1942 was a completely different generation of technology, as far advanced from the CXAM as the CXAM was from visual observation. The night of November 12th to 13th, 1942, marked the beginning of Japanese realization that American radar was fundamentally different from British or Australian systems. USS Helena's SG radar detected Vice Admiral Hiroaki Obe's bombardment force at 27,000 yards, a range at which neither British nor Australian radar could have reliably tracked surface targets. For 20 minutes, Helena's radar operators watched the approaching Japanese formation with perfect clarity, while Japanese lookouts, the finest in the world, saw nothing. When the battle began, American ships opened fire at ranges and with accuracy that Japanese officers found incomprehensible. Commander Tameichi Hara on the destroyer Amatsukaze experienced radar-directed fire for the first time and recognized immediately that this was not the primitive technology Japanese intelligence had described from captured British equipment. The shells arrived with mechanical precision from enemies firing in complete darkness through rain squalls that should have prevented any visual acquisition. This was offensive fire control radar of a sophistication that Britain did not possess and Australia had never attempted to develop. The technical specifications told the story of revolutionary advancement. The British Type 279 radar operated at 200 MHz with approximately 25 kilowatts peak power. Detection range against destroyers was 8 to 10 nautical miles with accuracy of plus or minus 200 yards in range and plus or minus 2 degrees in bearing. The display was an A scope requiring manual antenna rotation. Operational availability was approximately 60%. The Australian systems were essentially identical to British equipment, with similar specifications and limitations. They were adequate for their intended defensive purpose, but represented no threat to Japanese offensive tactics. A Japanese destroyer squadron attacking at night could close to torpedo range and launch devastating spreads before British or Australian radar could provide targeting information accurate enough for effective counterfire. The American SG radar operated at 3,000 MHz with 50 kilowatts peak power. Detection range against destroyers was 15 nautical miles with accuracy of plus or minus 40 yards in range and plus or minus 0.5 degrees in bearing. The planned position indicator display showed all contacts simultaneously in their actual positions. Operational availability exceeded 95%. Most critically, the SG radar was integrated with analog fire control computers and gun directors, allowing blind firing with accuracy, previously impossible even in daylight. The specifications revealed that American radar was not an incremental improvement over British technology, but a revolutionary advance into an entirely new generation of capability. Japanese technical officers who examined the specifications from intelligence reports initially refused to believe the numbers were accurate. Surely this was American propaganda or errors in translation. When captured equipment confirmed the specifications, the realization was devastating. The Battle of Tassafaronga on November 30th, 1942, provided temporary reassurance to Japanese commanders that superior tactics could still overcome American radar. Rear Admiral Raizo Tanaka's destroyer squadron launched a devastating torpedo attack against Rear Admiral Carlton Wright's cruiser force, damaging 4 American cruisers while losing only 1 destroyer. Japanese tactics had achieved victory despite American radar advantage. What Japanese commanders failed to appreciate was that American radar was still in its infancy, and American tactics had not yet adapted to the new technology. Admiral Wright had received excellent radar tracking of Tanaka's force, but made the fatal error of holding fire while he maneuvered for what he considered an optimal visual firing position. He was fighting with radar technology, but visual warfare doctrine. This was a transitional moment, not a permanent situation. American commanders would learn. Japanese doctrine had no capacity to adapt because it had no technological foundation. By early 1943, American tactical doctrine had caught up with American technology. Commanders like Captain R. Lee Burke and Rear Admiral Aaron Merrill understood that radar-directed fire was not supplementary to visual observation, but superior to it. They fought at night the way American bomber crews fought during the day, using technology to attack from beyond the enemy's ability to respond effectively. The results were catastrophic for Japanese forces. The Battle of Vela Gulf on August 6th to 7th, 1943, demonstrated American mastery of radar warfare. Commander Frederick Moosbrugger's 6 destroyers detected 4 Japanese destroyers at 11:33 p.m. from a range at which visual contact was impossible. Using radar alone, the American force closed to optimal torpedo range, launched coordinated attacks, and sank 3 of 4 Japanese destroyers without taking any damage. The engagement was conducted entirely by radar plot. Japanese lookouts never achieved visual contact with their attackers. Total Japanese casualties exceeded 1,200 killed. American casualties were 0. This result was simply impossible with British or Australian radar technology. The precision required for such a perfect victory demanded targeting accuracy, tracking capability, and tactical coordination that only American microwave fire control radar could provide. British Type 279 radar could have detected the Japanese destroyers, but could not have provided the precise targeting data needed for blind torpedo attacks and blind gunfire. The Battle of Empress Augusta Bay on November 2, 1943, provided another demonstration of American radar superiority. Rear Admiral Aaron Merrill's Task Force 39 detected Rear Admiral Sentaro Omori's superior Japanese force at 35,900 yards. The engagement that followed was a masterpiece of radar-directed warfare. American destroyers engaged at ranges exceeding 14,000 yards. In total darkness, scoring hits with their first salvos, they detected and evaded Japanese torpedoes using radar tracking of torpedo wakes, a capability that seemed nearly supernatural to Japanese observers. Despite superior numbers and firepower, Omori's force was routed with minimal American losses. Japanese post-action reports from Empress Augusta Bay revealed the psychological impact of fighting an enemy that seemed to possess unlimited vision in darkness. Officers reported that American ships maneuvered and fired as if it were broad daylight. Japanese torpedoes, previously devastating weapons in night combat, were evaded before they could strike. American destroyers appeared to know the exact position of every Japanese ship while remaining invisible themselves. The reports read like accounts of combat against supernatural enemies rather than human opponents with superior technology. The British and Australian navies achieved nothing comparable to these American victories because they lacked the radar technology to make such engagements possible. British destroyers in the Mediterranean and Atlantic fought with courage and skill, but never achieved the one-sided victories American destroyers routinely accomplished in the Pacific. The difference was not in crew quality or tactical doctrine, but in radar capability. American technology had advanced beyond what Britain had pioneered into realms British industry could not yet reach. The industrial and scientific gap between American radar production and British or Australian efforts was vast and growing. By mid-1943, the United States was producing approximately 1,000 SG radar sets specifically, plus thousands of other radar types. The Radiation Laboratory had designed over 100 different radar systems. American factories were manufacturing 250,000 cavity magnetrons. The monthly production of radio tubes exceeded 2.5 million units. 50,000 trained radar technicians maintained and operated these systems. Britain's radar production was substantial, but focused on defensive systems, particularly air defense radar for protecting the homeland. British industry could not match American production volume or invest in the continuous improvements that characterized American radar development. The SG radar evolved through multiple versions during the war, each iteration improving range, accuracy, and reliability. British naval radar development essentially stagnated at the level achieved by 1942, adequate for its purpose, but representing no advance toward offensive fire control capability comparable to American systems. Australia's contribution to radar production was minimal, necessarily limited by its small industrial base and population. Australian factories produced variants of British equipment under license, but undertook no independent radar development. This was pragmatic given Australia's limited resources, but meant Australian forces depended entirely on British or American radar technology rather than developing indigenous capability. Japan's radar production was catastrophic by comparison. Total production of all radar types during the entire war was approximately 300 units. The Type 22 surface search radar, Japan's most advanced naval system, had less than half the capability of the American SG radar. More critically, Japanese radar suffered from operational availability around 40%, meaning more than half the sets installed on ships were non-functional at any given time. Of the first 60 Type 22 radars produced, only about 6 actually worked properly. The cavity magnetron, that was the heart of microwave radar, remained beyond Japanese ability to manufacture reliably throughout the war. Japanese engineers understood the principles and had actually developed magnetrons independently by 1937, but could not achieve the power output and reliability American factories mass-produced. The industrial and materials science gap was simply too great to bridge while fighting a total war against opponents with overwhelming resource advantages. Japanese commanders gradually understood that they faced not just superior radar, but a comprehensive technological and industrial system they could not hope to match. British radar could be studied and eventually countered through tactical adaptation. Australian systems were no threat at all. American radar was connected to an industrial base that produced cavity magnetrons at rates exceeding Japan's total electronic component production, supported by research laboratories, employing more scientists than Japan's entire military research establishment integrated into fire control systems. Japan lacked the electronics industry to develop and continuously improved through systematic research programs that Japan's fragmented military research structure could never emulate. The psychological distinction was crucial. Japanese officers who examined British radar equipment captured at Singapore saw technology they could understand and potentially replicate. The systems were mechanically complex, but conceptually straightforward. Given time and resources, Japanese industry might develop comparable systems. This knowledge was not threatening because it suggested the radar gap was temporary and closable. American radar technology represented something different and more disturbing. The cavity magnetron required materials, science, and precision manufacturing that Japan could not achieve. The plan position indicator display required electronic circuits Japan lacked the components to build. The integration with analog fire control computers demanded mathematical sophistication and electronic engineering expertise that Japanese universities had not developed. American radar was not just ahead, but advancing faster than Japan could follow, the gap widening rather than closing. The Battle of Cape St. George on November 25, 1943, served as the final confirmation of American radar supremacy and Japanese helplessness. Captain R. Lee Burke's destroyer squadron, 23, achieved a perfect victory, sinking 3 Japanese destroyers without American losses or even significant damage. Burke's after-action report was clinical in its precision. The entire engagement was conducted by radar plot. Visual contact with the enemy was never achieved nor required. The Japanese force was destroyed by enemies they never saw. This result was simply impossible for British or Australian forces to achieve with their radar technology. British destroyers could detect enemy ships at night and gain tactical advantage from early warning, but they could not conduct blind engagements with such devastating effectiveness. The accuracy and coordination required for Burke's victory demanded fire control radar of a sophistication that only American industry had achieved. Japanese Naval General Staff orders from early 1944 acknowledged that night combat advantage now belongs entirely to the enemy. This represented complete abandonment of the tactical doctrine that had been the cornerstone of Japanese naval strategy since the Russo-Japanese War of 1904 to 1905. 40 years of training, tradition, and institutional knowledge were rendered obsolete by American technology. No such admission was ever made regarding British or Australian radar, because those systems, while capable, had never threatened the fundamental basis of Japanese naval tactics. The final accounting revealed the comprehensive nature of American technological victory. Between November 1942 and August 1945, Japanese destroyer losses in night surface combat exceeded 80 ships. American destroyer losses in similar engagements totaled fewer than 10 ships, most of those early in the period before radar tactics were fully developed. The exchange ratio exceeded 8-1, favoring America, a complete reversal from the early war period when Japanese night fighting skills provided tactical advantage. British and Australian forces never achieved such dominance because they never possessed the technology. British destroyers in the Mediterranean and Atlantic fought effectively and bravely, but never approached the systematic destruction American destroyers inflicted on Japanese forces. The difference was exclusively technological. American radar had evolved beyond what Britain had pioneered into a weapon system that transformed naval combat fundamentally and irreversibly. The broader implications extended beyond immediate military outcomes. Japanese military culture, rooted in samurai tradition and the belief that spiritual superiority could overcome material disadvantage, was forced to confront the absolute dominance of technology over human skill. British and Australian radar had never challenged these beliefs, because those systems remained tools that enhanced human capability rather than replacing it. American radar made human capabilities largely irrelevant in night combat. The finest lookout in the Imperial Navy could not detect ships beyond the horizon. The most skilled torpedo officer could not engage enemies who remained invisible. Courage, training, and warrior spirit meant nothing against oscilloscopes and magnetrons. Japanese post-war analysis struggled with this reality. How could a nation that valued technological innovation and had produced world-class optics fall so far behind in electronics? The answer lay in systemic factors British and Australians never exposed. Japanese military research was fragmented between Army and Navy with minimal coordination. University research was divorced from military application. Industry lacked the materials and manufacturing capability for advanced electronics. Most critically, Japanese military culture valued warrior spirit over technical expertise, ensuring that technical officers who understood the radar gap were ignored by operational commanders. Britain had faced similar challenges with inter-service rivalry and resource limitations, but had established effective coordination through institutions like the Telecommunications Research Establishment and practical cooperation, driven by immediate survival necessity. Australia benefited from British institutional knowledge and American technical assistance. Japan's isolation and institutional rigidity prevented the adaptation that might have narrowed the technology gap. The distinction between Japanese fear of American radar and dismissal of British and Australian systems ultimately reflected accurate assessment of capability and threat. British and Australian radar was defensive technology that provided early warning and tactical advantage, but did not fundamentally transform naval combat. It enhanced existing capabilities without replacing human skill. Japanese tactics could adapt to these systems through better training and tactical modifications. American radar was not merely an incremental improvement in naval warfare, it was a paradigm shift, a technology that cut so deeply against the assumptions of traditional seamanship that it rendered entire categories of human experience irrelevant. Conventional night fighting, an arena in which skillful officers could use darkness, intuition, and practiced coordination to outmaneuver an opponent, was transformed from a test of training into an environment dominated by electronic detection and automated fire control. In a very real sense, American radar did not enhance night combat. It ended it. It annihilated the concept of sensory limitation, destroyed the tactical meaning of darkness, and replaced human perception with machinery that saw with perfect clarity through conditions once considered the ultimate battlefield equalizer. To officers trained in the old ways, the shock was profound. Naval warfare was an institution built on the supremacy of the human mind and eye. For centuries, captains had fought by exploiting fleeting glimpses, masthead sightings, silhouettes in moonlight, muzzle flashes on the horizon. The Japanese Navy especially had refined these techniques into an art form. Their emphasis on night attack training, long-range torpedoes, coordinated destroyer assaults, and high-performance optics gave them, by the early 1940s, a genuine dominance in nocturnal engagements. Officers could predict the likely movement of an enemy formation by reading the sea and sky, estimating bearing changes in low visibility, and executing impeccable torpedo spreads guided by instinct honed over years of practice. But radar, true, microwave, centimetric radar rendered such forms of mastery obsolete. A radar operator in an air-conditioned compartment staring at a glowing cathode ray tube possessed more information than the most experienced night-fighting officer on the best-trained ship in the Imperial Japanese Navy. The machine did not rely on moonlight. It did not need a horizon. It did not strain its eyes. It did not lose track of targets in smoke, rain squalls, or the confusion of close action. It simply displayed positions, ranges, and courses with mathematical precision. Worse, from the Japanese perspective, the system fed that data into fire control solutions that allowed guns to track and shoot accurately without ever acquiring a visual target. This was not enhancement, it was replacement. The machine had supplanted the sailor. Japanese commanders recognized this grim truth slowly. Then suddenly, as the Pacific War unfolded, what had once been their greatest advantage, night fighting skill, turned into a strategic liability the moment the United States introduced the SG radar, a centimetric set capable of detecting ships at astonishing distances with remarkable accuracy. Their destroyers and cruisers, designed for swift night torpedo attacks, suddenly found themselves attacked and destroyed by invisible enemies who saw perfectly through the darkness. No tactic, however clever, could compensate for a sensor that nullified concealment itself. Commander Tamechi Hara, one of the rare destroyer captains who fought from Pearl Harbor to the war's final days and survived to write about it, understood precisely what had happened. In his memoir, he openly acknowledged that American radar, not American gunnery, not American seamanship, not American tactical doctrine, had ended the Imperial Navy's night-fighting supremacy. Hara had fought British and Australian forces as well, and while he respected their skill, their sensor technology did not inspire the same dread. He could manage British radar because it still left room for a highly trained Japanese destroyer officer to maneuver, deceive, and strike. American radar was different. It offered no such openings. It was, in Hara's words, and in the experience of countless other Japanese officers, absolute and decisive, a manifestation of industrial and scientific power on a scale that Japan simply could not equal. Japanese accounts from the war's middle years repeatedly describe a growing sense of futility. Officers who had once trained obsessively in night torpedo tactics watched those tactics become nearly suicidal. Ships advancing at high speed to launch their long-lance torpedoes, once the pride of Japanese naval engineering, found themselves tracked, ranged, and destroyed before they even realized they had been detected. The surprise attacks they spent years perfecting no longer surprised anyone. Radar-equipped American ships saw them coming from miles away, positioned themselves advantageously, and opened fire with radar-directed main batteries that struck home with chilling precision. The Pacific Oceans became a vast proving ground for this new technological reality. Every battle, every skirmish, every nighttime encounter served as another data point in the collapse of the old order. Early engagements, like the Battle of Savo Island, where American forces lacked full radar integration and suffered catastrophic losses, offered Japan a fleeting glimpse of what might have been a Pacific War fought in darkness where human skill still dominated. But by late 1942, and increasingly through 1943 and 1944, the United States Navy fielded SG radar widely among its cruisers and destroyers. With each month, the gap widened, not only in the number of radar sets deployed, but in the way American naval doctrine evolved to take maximum advantage of them. One of the most devastating consequences for Japan was the shift from radar as a detection tool to radar as part of an integrated combat system. To Japanese officers, radar initially appeared to be a kind of supercharged searchlight, a device that allowed early warning but still required traditional visual confirmation before engaging. They assumed, incorrectly, that radar simply enhanced existing capabilities. American radar doctrine was very different. Radar did not merely locate enemies. It served as the backbone of a system that connected detection, tracking, plotting, and gunnery into a single, unified process. No human sensory input was necessary. A destroyer could fire its guns with accuracy at targets it had never seen with the naked eye. A cruiser could track multiple enemy vessels simultaneously and direct fire on the most threatening one instantly. Fire control radars locked onto targets and held those solutions even during radical maneuvers or in the chaos of close-range engagements. The effect on Japanese crews was psychologically devastating. Ships exploded in the dark without warning. Salvos arrived without detectable origin. Destroyers found themselves bracketed by perfectly timed American fire before they even finished unmasking their own guns. The enemy appeared to possess an impossible degree of awareness, a supernatural vision cutting through smoke, rain, and moonless night. But it was not supernatural, it was industrial. Japan could not mass-produce centimetric radar sets. It lacked the manufacturing base, the supply chain, the materials, and the highly specialized engineering capacity. American shipyards, laboratories, and factories, by contrast, generated radar equipment in thousands of units, iterating rapidly through improved designs and continually refining doctrine based on combat experience. Every new generation of SG radar appeared in greater numbers, on more ships, with better integration into combat information centers. Japanese officers, increasingly aware of their technological inferiority, could only watch as the United States converted industry into decisive battlefield dominance. The waters of Iron Bottom Sound, the Solomon Islands, the Central Pacific, and eventually the Philippine Sea witnessed this transformation repeatedly. American destroyer squadrons demonstrated the frightening efficiency of radar-assisted combat. At battles such as Cape St. George, often cited as the purest example of radar-developed night engagement, American ships attacked with complete situational awareness, orchestrating movements with mathematical precision, while Japanese destroyers stumbled blindly into gunfire they never saw coming. For the Americans, the battle became a demonstration of engineering supremacy. For the Japanese, it was a moment of revelation. Night fighting, their proudest accomplishment, belonged now to the enemy. The darkness of the Pacific, once the silent ally of Japanese tactics, had been technologically conquered. Radar deprived them of their identity as masters of the night. Their decades of doctrinal development, their investment in superb optics and extraordinary training, their faith in torpedo attacks perfected over generations, all of it collapsed under the weight of a single innovation that rendered concealment meaningless. Tradition had been overtaken by electronics. Art had been replaced by system. Again and again, Japanese destroyers attempted night forays, only to be repelled or annihilated by American ships that saw them long before contact. Radar-directed gunfire turned the night into an American hunting ground. Japanese accounts frequently describe the disorientation of being attacked by ships they had neither expected nor detected. Officers who had once trusted their senses now doubted their own perception, uncertain whether the sea itself had betrayed them. In many ways, this transformation encapsulates the entire technological dynamic of the Pacific War. Japan entered the conflict with superb tactical training, excellent equipment in specific categories, and an institutional culture that prized skill and discipline. The United States entered with industrial capacity, scientific infrastructure, and a willingness to integrate complex technologies into every level of warfare. Skills could be taught, but the industrial system that produced radar, a system capable of mobilizing thousands of scientists, engineers, and factories, could not be replicated by a nation whose industrial base was a fraction of America's size. American radar thus became the symbol and instrument of a broader reality. Industrial warfare favors the side that can harness knowledge, production, and technology at scale. The Imperial Navy's night fighting tradition was a masterpiece of human craftsmanship. The American radar system was a masterpiece of collective industrial power. In a prolonged war, the latter proved categorically superior. By late 1944, Japanese commanders no longer hoped to regain night fighting superiority. They understood that the era of the skilled human night fighter had ended. Radar had redefined naval warfare. Darkness was no longer a shield nor a tactical environment. It was simply another domain mastered by those who possessed the machinery to pierce it. In the end, the Pacific War demonstrated a truth that Japanese officers like Hara articulated with clarity and a sense of bitter finality. The battlefield belongs to those who see first, and strike accurately. American radar ensured that the United States could do all three, regardless of conditions, training, or the bravery of its adversaries. The night, once ruled by Japanese destroyers, had been taken from them, quietly, relentlessly, and inevitably, by the glowing screens of American radar operators and the industrial machine that placed those screens aboard hundreds of ships across the Pacific. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.